we actually cross a sort of dividing line, and we go to a regime where the interaction is such that material somehow is removed from the sample. So we have a more aggressive interaction. So if this is happening, the material removal is equivalent to sampling, and the interaction of that sample with the laser can also be considered as excitation. So if the interaction is basically the energy density is relatively low, we can remove through ablation or desorption material from a solid sample, for example, and analyze this through mass spectrometric tools. If the energy is higher, not only do we remove material, but also we excite this material. And in that case, we form plasma, and we generate a different technique, which we call LIBS, laser-induced breakdown spectroscopy, and we'll give a few examples of this in a while. So mobility and remoteness are the concepts we're talking about. What we see on the screen, basically the Perseverance rover of NASA that has been launched since 2 years back on the Mars, is a beautiful example of remote sensing and mobile laboratories or mobile spectrometers. I would like us to concentrate our attention on the SuperCam module on the rover. It says here laser micro imager. So there's a number of functions in this head here. One is a high resolution imaging at distances of the order of 10 meters, average distances of the order of 10 meters. So one can image rocks and stones and other features on the surface of Mars. Then there are two different laser systems. One is a visible laser, and through a telescope can be focused on the surface of the area selected and perform Raman measurements. The other is a pulsed laser and can perform LIBS measurements. So this is really a beautiful example of remote and mobile analysis altogether. So since we're talking about remote sensing or remote analysis and mobility, let's see roughly how these two can be implemented. On the left-hand side of the slide, basically we see a typical example of a ground-based unit loaded with lasers and spectrometers, and the essential part of it is a laser beam that is directed over to the sky and meets several changes or disturbances of the atmosphere, for example, smoke and other pollutants. The basic principle of this laser remote sensing, or LiDAR sensing as we call it, is that the light is transmitted through the atmosphere, but at each and every point along its path length, some of it, a small fraction of it, is scattered backwards towards the unit, towards the detector. So we'll show some detail in a minute. But basically, through the backscattering, we can collect information from various heights or from various parts of the beam path. We can understand that if we record the backscatter intensity, that drops with distance, and that is a consequence of the collection of light. The further away the source, the less light we collect. But sometimes we see further reduction of the backscatter light because at some point along the path there is some substance, some smoke, some whatever that is partially absorbing and therefore reducing the intensity of the beam, both ways. And in fact, if we do this right, we can actually get a spatially resolved distribution of the pollutants. We know which pollutants we have because we know how to tune our laser at certain wavelengths. Now, we'll see some more on the instrumentation in a minute for laser remote sensing. On the right-hand side of the slide, we see a mobile system. It's not in an industrial or environmental application, it's on a heritage application. This is something that we do in our lab, and I will show you some examples. But what you see here is basically a snapshot of a campaign we had some years back in the Archaeological Museum of Heraklion, looking at the pigments of that ancient wall painting. What you can see right over here where I'm pointing the pointer is basically the head of a mobile Raman system. This mobile Raman system can fit in these two suitcases here. The head I was talking about is exactly this one. So this is the one that comes close to the sample and does the analysis. There's also a spectrometer and the laser and other optical components. So this is mobility because we're talking about compact instrumentation which can travel. We can take it with us and satisfy field applications in a way. So let's have a look at the basics of the remote sensing instrumentation. Of course, there are different approaches, but the idea is roughly the same. You have a source, a laser source. In this particular case that I'm showing on the left-hand side here is a excimer pump dye laser. So we can, through appropriate optics, telescopic optics, shoot the beam over to the atmosphere and then collect the backscattered light. So through the telescope, we collect the backscattered light. It goes into a spectrometer and detector. Therefore, we can record spectra, or we can record intensities at particular wavelengths, or we can do both. And this way, we can analyze various pollutants in the atmosphere, identify them, measure them, and so on. A variant of this, which does not really contain lasers, is the satellite imaging instruments that there are plenty of those nowadays, and they do environmental work. So they are tuned to particular transitions, molecular transitions, and measure greenhouse gases and others. A slightly modified version of what I just showed you is the one that is on the right-hand side of the slide. This is something that we have done in our lab, and it's not a collinear version, meaning that we don't have the laser beam and the backscattered light along the same way. This is basically for relatively short to medium distance applications, 10 to 50 meters maximum. So we do have a pulsed laser beam, for example. We adjust it with special optics, and we can focus it at a target further down, about 5, 10, 15 meters. The result of the interaction, in this particular case, it's plasma formation. The result of the interaction, or the emission from the sample, from the surface of the sample, from the surface of the target, is collected offline with a telescope, which is actually focused over there. Through an optical fiber, we can take this emission into a spectrometer, analyze it, measure it on a detector, and obtain spectra. I will stay a little bit on this example. You see that our target is actually an insulator, and I will show you what insulator I mean. It's right here. These are high voltage power lines, and among the various wires and cables that we have there, we have insulators, which I'm showing on the slide. These insulators are made of silicon rubber, and sometimes they sustain a heavy burden, and we have phenomena like this one. This is called, in the jargon of the power line electricians, it's called flashover. So basically, you have a discharge all along the insulator. This is common thing, and this is induced by atmospheric pollution plus humidity and so on. But this flashover actually changes the surface of the insulator and changes its hydrophobic capacity. It's important for these insulators to be highly hydrophobic so that water does not really stay on them. And this is something that needs to be checked periodically. The way that this is done is basically to stop the transmission and take down the insulator and take to the lab. But you understand that this can be detrimental to the maintenance of the network. So having something that can be done on site and online is something that we very much like to have. So let me just go back one slide, because I want to just say a few words about this LIBS technique, which I mentioned a minute ago. This is, again, laser-induced breakdown or plasma spectroscopy. We use a pulsed laser, typically nanosecond pulse width. We focus it on the object, the sample, the target. In a case, could be the insulator we mentioned. Plasma is formed on the surface. We collect the emission from the plasma into spectrograph and a detector, and eventually we get a spectrum, an emission spectrum, which is an atomic emission spectrum. On the basis of the lines, we can identify the presence of certain elements. On the basis of the intensities of those lines, we can get information about the concentration. The latter requires a little bit of calculation to take into account the plasma temperature and so on, but in principle, it's something that can be done. So what we had with the insulator is that we get its spectrum. What you actually see is obviously silicon lines and other titanium and sodium, obviously from environmental deposits, because these insulators are close to the seashore. As I said, the insulator material is PDMS, or silicon rubber, as they call it. So it's a highly hydrophobic material and highly insulating material. With the flashover problem, what happens is that some of the methyl groups on the PDMS go away and are replaced by hydroxy groups. So that reduces hydrophobicity or increases hydrophilicity. This is something that we need to be able to monitor from far away. So if we there's certain techniques like FDR spectroscopy that's possible, but with the LIBS technique, we can do it from far away, and in fact, concentrating our attention in a narrow range of the spectrum, we identify an emission line from silicon, and we identify an emission line from what you see here, CN. CN forms during the plasma formation process because of a reaction of the carbon atoms with nitrogen in the atmosphere. So effectively, the emission of this CN species reflects the amount of carbon on the sample. So basically, we look at the ratio of carbon or CN, if you like, to silicon through this indicator, and that reflects the health of the insulator. So when the CN to silicon ratio is over a certain value, a threshold value, then we know that the methyl groups are there and the hydrophobicity is at the level where it has to be. When this indicator drops, and we observe this in aged insulators and so on, that indicates that the silicon rubber has actually lost its insulating capacity. So this is something that we have been working in the past years, and actually now recently with collaboration with other groups in a company, we try to make an integrated LiDAR system that will be doing LIBS on insulators on actual power lines. I will move on to something which is more relevant to our project, plastic waste sorting via Raman spectroscopy. So this is a quick example that indicates how plastics, in fact, in the recycling unit, those plastics are actually broken into smaller pieces. They might contain metal components as well, so they get into a pre-processing unit. The metals are, because are heavier, are going away. The plastics are collected, aligned over a conveyor belt. There are some monitoring tools to actually look at where those pieces are, and these tools give the go to a Raman spectrometer, a Raman probe, that is located over the conveyor belt and performs the analysis. For typical electronic household plastics like polypropylene, polystyrene, or ABS, you can see the spectra that the authors of this paper have shown, and it's possible to differentiate among these three spectra using certain algorithms. So through the through the control unit, very quickly, as the conveyor belt carries over the pieces and the Raman spectra are collected, we can identify those pieces and then give a command to an air gun or another unit and separate different materials, different pieces of plastic. So not only they do recycling, but they actually sort the different waste so that they can be distributed accordingly. We know that the enemy of Raman spectroscopy is fluorescence. So a drawback of this technique is that if you have fluorescent waste plastics, they will not be recognized. The reason they use a long wavelength like 785 nanometers is basically this, to avoid fluorescence, but this cannot be avoided all the time. But this enemy can, in fact, be turned to an advantage if we look at the same problem with a totally different perspective and try to consider fluorescent plastics. Now, not all plastics, commodity plastics, are fluorescent. However, the proposal of these authors is to actually add very small quantities of fluorescence markers in various plastics. In fact, combination of fluorescence markers which will encode certain information. So as long as we have that information encoded to the fluorescence of the plastic, then we can do again the sorting, and with certain imaging units identify those pieces along and across the conveyor belt, then use a laser beam or UV light to excite the fluorescence, and with cameras to collect the different emissions and then sort them accordingly. Now, to explain a little bit further this concept, I'll take you to this slide where we indicate that we have different markers, different fluorescence markers in different plastics, and based on like 4 different marker fluorophores added, I repeat, added to very low amounts, very low concentrations. In fact, one could consider encoding of fluorescent information that is related to the actual plastic, and therefore by using, for example, 4 different markers, one can produce 16 different codes for the plastics and do accordingly the sorting. So there are plenty of ideas like that out there. So not only solids, but also gases can be probed from far away. And I'm happy to show this particular example, which comes from FORTH and the group of Michael Velegrakis in our institute, along with work from Panos Iosos and Yannis Psilakis. You see, these guys have been using, they made and have been using an open path system, tunable diode laser absorption spectrometer to monitor greenhouse gases over in the environment and over fields with related to agriculture. Basically, by using different types of infrared lasers, they can probe various gases like CO2, methane, and one can probe water and other things. The idea here is that you have the different lasers. We have fiber collimators, and basically you send in an open path configuration the laser beams along a path, and as long as along the path there's a target, and this target can be a tree or so, there is backscattering. So that backscattering is collected in a telescope and detected. And again, here by tuning the laser along across a spectral transition, one can take spectra, characteristic spectra, absorption spectra, for example, methane, water, and so on. These lines that you see here are very narrow. They are actually rotationally resolved vibrational lines. So they come from overtone and combination vibrational transitions, but at particularly with particular rotational resolution. So this group can measure average concentration of pollutants like CO2 or methane along the way, and you see the data collected for a number of days back in earlier this year and late last year are in certainly quite good agreement with data collected from the tropospheric measurement instrument, which is a satellite imager and satellite-based spectrometer. So again, you see that these things can be done. This concept can be used for remote analysis of gases and pollutants. We move over now to mobile spectrometry, which we mentioned a while ago, and I wanted to just concentrate for a while in the instrumentation concept. So in all mobile systems, basically what you have is what we call a probe head, and this is a unit with optics and perhaps laser detectors that its task is to couple optically the excitation light to the sample and couple the backscatter light into the detection system. The backscatter light can be simply reflected, can be inelastically scattered, for example, giving rise to Raman signals or fluorescence emission. So we can see on the left hand side of the slide the mobile Raman microspectrometer. This is something that we have in the lab, but it's a common instrument, probe head. And there is a laser source, which is fiber coupled to the probe head through a number of optical parts inside the probe head. The beam is directed through an objective lens onto the sample. So this microscope objective actually turns this spectrometer or this probe head to a micro probe. The interaction of the beam with the sample produces Raman scatter light that is collected through the same objective and along the same path goes back, but manages to go through a special filter. We call it edge filter. It's highly reflective to the laser pulse, to the laser beam. It's highly transmissive to the Raman shifted backscatter light through a lens coupled into an optical fiber, transmitted into a spectrometer, and this way one can record the Raman scattering spectrum. There are different sorts of probe heads which can be adapted to various applications and can be adjusted to various instruments and various measurements, including industrial environments, online measurements for monitoring industrial processes and so on and so forth. A slightly different concept that is actually a commercial instrument is the handheld instrument, which again is a probe which is handheld. In this particular case, it's a LIBS probe, which is used for metal scrap sorting. So on the back, the user holds this, fires the laser, gets some information on the back. This information is sort of coded or simplified and gives the user the idea about what is the metal that they are probing, and they can sort it manually. Sometimes manual sorting is also relevant and important. I show you here a mobile spectrometer, a LIBS mobile spectrometer, which we have developed in our lab, and we use it primarily in cultural heritage applications, but in principle, it's something that can be used for other applications and cases as well. So you can see clearly this little piece here. This is the probe head. It does contain the laser. It does not contain the spectrometer. The spectrometer is connected to it through a fiber. So, and I'll show you an example. I'll show you how roughly this works. This is the interior of this probe head. You can see a small Q-switched ND-YAG laser that produces nanosecond pulses at 1064 nanometers. The beam is directed through a pierced mirror onto a target object. Over there, it forms the plasma, and the plasma emission is actually collected backwards through the same lens, reflected onto the mirrors, and coupled into the optical fiber that takes it to the spectrometer, and we record the emission spectrum. Now, how do we do that? You see in the slide again a mobile Raman system and a mobile LIBS system working in a museum side by side. So, and it's easy, straightforward to see the concept. We have the Raman probe head on the left. We have the LIBS probe head on the right, and they do their analysis. We can work in parallel. We don't have some way to go at exactly the same point. However, both instruments are equipped with cameras, and we can find roughly with very good accuracy and go and point at the same area, first with one, next with the other. So I'll take half a minute to show you a relevant LIBS spectrum for the analysis that we just described in the previous slide. So a typical LIB spectrum is full of narrow atomic emission lines, and those more or less identify the material that is the composite material that you have. You need to be somewhat educated and have, or make at least some educated guesses. But because the material that we were probing had a yellow color, the pigment was yellow, so we looked at lines which come from lead and lines, emission lines that originate from chromium. The combination of these two, along with the fact that our material, our paint, our substrate was yellow, gives rise to a positive analysis for this compound, which is called lead chromate, and it's a well-known yellow pigment. But not only that, in some small, really small lines over here, over here, we see features like gold, for example, and copper and silver, and this indicates the presence of a gold foil. This was barely visible through an optical microscope, but we had a hint, and clearly we detected the presence of the remains of a gold foil. There are several other lines coming from calcium or aluminum, and these originate either from the stone or from additives of the pigments. So you can see that one can have rich information from a single spectrum. I'd like to emphasize that the spectrum we see here is a single laser shot spectrum. It's not an average spectrum or anything like that. Of course, in parallel with this, one can have information coming from the Raman system, so we can combine analytical information towards making a more complete analysis. This is calling for combination of techniques, combination of probes, and sometimes incorporating these different modes in a single instrument is convenient. So what I'm showing here is the latest achievement of the group. It's like a few months old, and what you see on the top left of the slide is actually something that came out of the lab like last month, and it's a system that combines three techniques. We call it triena in Greek, trident in English, if you like, in a single probe head and a control unit. So the techniques combined include LIBS, include absorbance or diffuse reflectance, if you like, and include fluorescence emitted following excitation with a lead source. Removing the dressing from those instruments, you can see the inner part, both of the probe head and on the spectrometer and control unit. You see it also in the lab, along with those people in the lab who actually contributed and were responsible for this engineering and development project that was funded by a project we had with the archaeological authorities in Athens. Leaving the environment of the museum, which is rather convenient, one can actually go to much more demanding or hostile environments, for example, the Antarctica, and this is a campaign by Valentina Raimondi a few years ago in Antarctica, using a portable fluorescence probe. So again, the same concept, a blue laser, a blue diode laser is the excitation source. A spectrometer provides us with spectra. Both the laser excitation light and the emitted light are transmitted through optical fibers. So there's a slightly different approach with respect to the ones we saw a while ago. Now we have fiber optic probes which actually transmit the light all the way to the target surface, to the sample surface, and collect the emission. In some examples, as we see on the bottom of the slide, there are clear chlorophyll emissions from microbial growth on biological crusts found in Antarctica. In other clean rocks, there's emission from the rock minerals, and many other things can be done this way. Obviously, with the Raman system, one can see other things, but fluorescence is a very sensitive technique and quite often provides critical information in a straightforward and fast and easy way. There are a little bit more demanding spectroscopies like the cavity ring down scheme, which are being used again for environmental monitoring. For example, what we see on that slide is monitoring of moisture. The system again depends on a laser diode, which enters a cavity unit, which you see over here. I will explain in a minute what this cavity does, or what cavity ring down spectroscopy is. That chamber here contains the gas, and by looking at the signal, the cavity ring down signal on a computer, one can find out or can quantify the amount of moisture. This is quite compact system, as you see over here, less than 25 centimeters long, and definitely mobile. The data which we see on this spectral line refer to water, and again, this is a rotationally resolved line of vibrational overtone transition, a beautiful calibration curve of the cavity ring down signal over the reference sample, and the capability of the technique goes down to a few ppb capacity to detect moisture in air or in other gaseous environments. I need to show you, because not too many people use this technique. I need to show you roughly how it works. Imagine that we have a laser pulse entering a cavity composed of 2 mirrors with very high reflectivity. So if the mirrors are very highly reflective, so the beam will be going back and forth, left and right into this cavity. Because they're not fully reflective, a small percentage of the beam will be coming out each time for its round trip. So if we monitor the pulse coming out following the first passage, and the second round trip, and the third round trip, we can have a feature like that. The arrows indicated here are displaced for clarity. In fact, the beam can be collinear in here. So the decay of the signal gives rise to a characteristic cavity time. So by looking at this signal, we can find out information about the absorbing media. Now, the only thing that we need to look at here is that this red part of the equation on the bottom of the slide, the inverse of the cavity time as you see it on the top, equals the inverse of the cavity time when the cavity, when the cell is empty, or when there's no absorber in there, plus the absorbance of the sample times the speed of light. The absorbance of the sample is basically absorption cross-section times number density of the gas, thereby by tuning the laser beam into a proper wavelength so that we have a healthy absorption cross-section, we have strong absorption, we can actually achieve measurement of very low number densities or very low concentration of gases by using this technique. Hence, the very low detection limits in the order of a few ppbs of moisture in the slide that we saw previously. I think we're more or less finished. Yeah, I wanted to show you one last thing from a relatively recent communication. There is an increasing number of applications using basically smartphone technology. And what I show you here is a recent publication from a group in China where they do LIBS analysis of minerals by using a very, very simple configuration. They have a small pulsed laser which actually is focused on the mineral sample. As you see here, then the light is collected with a lens, collimated and sent into and through a transmission grating. It's a transmission grating, not a reflection grating, which is in a module attached on the back of a smartphone. So the line is analyzed through the grating, and then with a mirror is focused on is directed onto the lens of the camera and is detected by the camera. By calibrating the pixel number of the smartphone camera with certain known lines, one can actually get spectra of those. You see spectra more or less here. They can get spectra of the plume emission, the plasma emission, and identify various minerals. These sort of applications range from cover various spectroscopies, and they can be used with absorbance or fluorescence or Raman spectroscopy coupled to smartphones. I think this is more or less it, and I would like to thank you very much for your attention, and I will be happy to answer questions if they exist.
Will you stop sharing?
I will stop sharing and look at
The chat section.
the
Maybe
chat
there.
section. Yeah.
Yeah. While we wait for some questions, I will very briefly mention that in a couple of minutes you will see a survey link on the chat that we ask you to answer a couple of questions about this webinar and what you would like to see in the future. And please, if you could fill this in, it will be very helpful. Okay, so any question for our speaker? Okay, then if not,
There is one question, Mary,
there is one. Okay.
in the Q&A.
Okay. So we have an attendee that asks if the compact CRDS spectrometer can be used for analyzing moisture permanently in various chambers.
Well, I would say if the laser beam can be properly coupled in a chamber, that can be done. However, this unit, the cavity, as we showed it, should be installed within the chamber, and there should be a way to couple the laser light with the fiber into the cavity. In fact, I didn't note that in the particular application the laser used is CW laser, not a pulsed laser, but the concept of the cavity ring down is the same. A CW laser is much less bulky and much easier to use compared to a pulsed laser. The cavity ring down technique is quite advanced, and there's even commercially available systems used for various applications. So with some appropriate modifications, I'm confident that one could use them for probing moisture in various environments, including chambers.
Thank you, Dimitris. Any other questions? Okay. So if not, I would like to inform you that the next presentation will be given in the 1st of September, and it will be given by Eric Hirschman, and it will be an overview on non-destructive material analysis using positron annihilation spectroscopy. You can find the information about this event and the future events again on our website. And in case you didn't have the opportunity to fill in the survey at this time, you can find the link in the description of the YouTube, where this presentation will also be available. So again, thank you very much for your attendance. And if there are no more questions, we will finish this webinar at this point. Thank you very much for attending.